So I want to talk about machine learning for quantum simulation. And so this is what quantum condensed matter research community tries to do. That is, we try to go from complex experimental data, such as scanning probe or X-ray or neutron scattering bulk probe, or even database of material properties that's been curated. We would like to go from complex data to theoretical insight. At some level, this is sort of what model reduction is also trying to do. You're trying to go from very detailed reality to some manageable model that can be solved in some way. But I will be stepping a little bit farther out to start from experimental observations. And I want to try to get to some theoretical insight starting from experimental observations. And because this is a reductionistic process, as in model reduction, much talked about in this conference, the only way we can have confidence that we've kept the right ingredients in without throwing the baby out with the bathwater is to be able to make prediction and predict the next measurement. Now, this is what the community have always wanted to do. And this process has become much more challenging with revolutionary expansion in data. So the data revolution from experimental perspective came in several fronts. For instance, tunneling density of states is measured by I don't know why my computer is freezing. Measured by making a macroscopic tunnel junction where, for instance, here superconductors are sandwiched with normal metal or insulator in the middle, and you apply a voltage. There will be quantum mechanical tunneling through the barrier, and the measurement of would be one scalar quantity that's plotted as the voltage is varied. Plots like this, for instance, here shows suppression of the density of state. It shows the coherence peak, but not only these salient features, but even the subtler features, such as this little blips, were understood. And knowing how to think about all features of this data gave us confidence about confidence in the BCS theory of superconductivity. But fast forward to today, instead of a single curve, my experimentalist colleagues would easily measure tens of thousands of curves, because at each point in position, they will make a tunnel junction that is at atomic scale and make tens of thousands, 100,000s of curves. And we cannot open any textbook to figure out how we should handle, how we should go reduce such data to some insight. X-ray diffraction, a problem that is famously involving inverse problem. In 1913, in this Nobel Prize winning paper, father and son Bragg and Bragg came up with the very first forward modeling. They said, we can explain three peaks that they observed if we assume the atoms are arranged in a periodic array. And if we think about the interference between these two paths, we can make a model that depends on one parameter, the distance between the plane. And by fitting the measurement to the model, we can infer what this distance is. This is the first successful example of forward modeling for X-ray diffraction. And it was so successful, now we teach this in introductory physics. Now, but you fast forward to today, instead of three peaks, our colleagues would measure 100,000 people. And now one can have statistical understanding of what's happening from one drag peak to the next, but we don't have a procedure for extracting information from this volume of data. What I want to actually focus on today is projective measurement, because it comes closer to sort of computational work that's much discussed in this conference. Although I'm not going to be talking about computational data, it is sort of a computation, or one day it will be a computation, in the sense that I want to talk about quantum simulation. So projective measurement in 1920s, done by Stern and Gerlach in this famous plaque, shown in this plaque, and this is the original data. The splitting of the beam tells us about the two-dimensional Hilbert space associated with spin half. Single spin half has two-dimensional Hilbert space. Each time the silver atom comes, it will either end up at the top or at the right or on the left, and each of those are projective measurements. It's either ending up here or ending up there. Now, fast forward to today, instead of having one spin half that is two-dimensional Hilbert space, one could be looking at Hilbert space associated with 256 spins. So now we are talking about enormous 2 to the 256 dimensional Hilbert space. And the projective measurements will be not of a single spin, but of all these qubits. Now, here I'm showing what the stacks of these projective measurements will look like. When we had a single spin half, we could model what the measurement outcomes are saying, and based on that model, we could infer the Hilbert space, and we can learn the density matrix if we do enough projective measurements. That is the probability distribution. Also, we need to do rotation in basis to actually learn the density matrix. But with this large Hilbert space, actually learning the density matrix, which is the full tomographic task, is impossible. It's just simply impossible. So what can we do with this kind of data? My group have been trying to make the connection between complex data and theoretical insight, now including quantum simulator data, using machine learning tools, because we are looking at all these problems as data science problems, data problems. And we've been looking for opportunities that machine learning approaches can make a difference and contribute to scientific progress in many different types of data, scanning probes, spectroscopy, sometimes even simulated data from when you can have imaginary time data and wanting to learn about transport. And what I want to talk about today, it has to do with quantum gas microscopy, or projective measurements on quantum simulation of the Fermi-Hubbard model. So what am I going to use? I'm going to be using machine learning tools, and I will be using neural networks. I've been told that I should try to make the talk sort of self-contained, making sure there is enough introduction. So just to make sure that everybody's on the same page, I'm going to give a sort of a rudimentary introduction to how neural networks work and how we will use that to learn what's underneath the projective measurement. So here is a starting point. We have a very simple neural network. This is fully connected multi-layer perceptron with a single hidden layer. And this is architecture one can use to get to about 95% success in handwritten digit recognition. You train all this handwritten digit data train the neural network using the label data from 0 to 9. And then once the neural network is trained, it will be able to recognize the handwritten digits. Now we wanted to use same kind of approach, looking at experimental data and testing different hypotheses. So if we have different hypotheses, we will train the neural network with data associated with different hypothesis options, and we will give actual experimental data to test how well which of the options capture the data. And the idea is that the neural networks are making a decision. It's going to make a decision among the multiple choices that it has. And the decision-making process is very much like decision-making process this kid will go through. So this kid who has to make a decision about what to do about the food that has dropped will take inputs. It could be how long it has been, how long the food has been, is mom or whoever is the bad cop in the family is watching, how sweet is it, how green is it. These are some of the inputs that appears to be important, for instance, for my kid decision making. There will be an output, which is whether to pick it up and eat it or let it be. This is a binary outcome. Now, when we go on to looking at quantum simulation data, we can be using binary outcomes, asking, is this a phase that I trained you for? Or is this something that you understand it to be the same or different? These are binary questions we can ask. We can also ask multiple choice questions. But the whole procedure is very similar, irrespective of how many choices are given at the end. Ultimately, the whole neural network is a mapping between the set of inputs and the output. So different parts of the brain, that poor kid's brain, will weigh these inputs with different weight. So this weight is specific to the input component and to the neuron itself. So this is a matrix. And each neuron will commit its own bias, and there will be nonlinear firing. So the sigma is a nonlinear function as plotted here. And the idea is different neurons would have individually different weight matrices and different biases. So decision is uniquely determined once the weights and biases are fixed. But we are not going to try to figure out what is the good weight and bias by trying to have a manual analysis of it. But we will just give a lot of feedback and let the neural network learn what is weight and bias that ends up being that leads to the decision that is approved. Very much like I cannot write my kids' brains, but I can give them feedback. Similarly, we are giving feedback to the neural network, and ultimately, neural network will be a function of this sort. The appeal of using neural network is that, in principle, there are theorems showing that neural networks can be arbitrarily expressive. That is, you can write a very complex function with it. So if the mapping between the input data and the output is expected to be complicated, working with these functions that are in principle possible to learn very complex functions is appealing. So the training process for this particular exercise would start with having a label training set. So these are circumstances under which it is okay to pick up and eat it, and these are circumstances under which you should let it be. And there will be desired output associated with each of the training sets. And the key part of the training is to have this cost function. So the cost function is measuring the distance between the neural network output and the desired output. So the neural network will be trained by trying to minimize this cost through stochastic gradient descent. So through the gradient descent, the weights and biases, the parameters of the network will be learned while minimizing the cost function. So this is all great, but answer being correct does not guarantee the thinking process being correct. And as physicists, we would like to be right for the right reason. And if we're using neural network, we would like the neural network to be right also for the right reason. So interpretability is important, but that's a challenging task. So this we have came up with architecture that is simple in its structure and designed to be interpretable. You can find more details. Where's my mouse? In this paper, Nature Communicator, right here. Somehow, and yeah, there's the paper. And this was collaboration between my group and my collaborator in computer science at Cornell and my collaborators at Harvard. So the Fermi-Hubbard model, this is the model. And it's a model of interest because many of us in the community believe that this model has the gist of complex phase diagram that materials like high-tissue cuprates exhibit. And the experimental community simulating the Fermi-Hubbard model on optical lattices have, over the course of last 10, 20 years, been able to actually cool down enough that they start to see antiferromagnetic fluctuations, and they start to be able to explore this parameter regime. The quantum gas microscopy works by loading the atoms, simulating the Hubbard model, and what you get is snapshots like this. There are three outcomes, three states here that each site is being projected to spin up, spin down, and hold. We the architecture that we have developed to optimize interpretability is built on typical convolutional neural network, but we have adapted it for the interpretability sake. So typical convolutional neural network take the image data or input data, and it will use a convolutional filter and make another image that is the input data convolved with the filter. So this C of X is a convolutional map. Once you have this convolutional map, although there can be many different variations that you can implement, the key thing that is common to all convolutional neural network is to take this convolutional map and eventually put it through a nonlinear step, and out comes the decision. The convolutional process itself is a linear process, so that is very easy to take it apart. It's this nonlinear step that makes typical convolutional neural networks difficult to interpret. And my student Cole came up with this idea that perhaps we can replace the full nonlinearity with powers, polynomials. So if you take C1, which is a convolution, and then make C2, which is a second power, and third power, and on. This way, we can have control over the degree of nonlinearity, and we control each power separately. Then we can learn what level of correlation is actually important for defining a given phase. So this is what we call correlation convolutional neural network, CCNN. We applied this to first to simulated data, where we were comparing two ground state ansatz for the Hubbard model, that is geometric string and pi flux theory. Working with the synthetic simulated data, what it means, what we're doing is considering wave functions and trying to see whether we can distinguish the wave functions. Of course, if we are writing the wave functions by hand, we know they're different. But we want to put ourselves in the position of what would it be like to look at the experimental data, because that's what we ultimately like to do. And when we are trying to look at the experimental data, there is limitations in what we can know. Specifically, we can only look at projective measurements. And projective measurements of two wave functions, even if they are constructed with very different philosophies, may or may not be distinct enough to be told apart. And we may not necessarily know, although we were able to write down the wave functions, we may not know how to distinguish the two. What operator or what measurement will distinguish the two. So what we were able to do is to train our convolutional neural network to distinguish snapshots made from this wave function, geometric string, where we imagine the antiferromagnetic background is frozen at the time scale of the movement of the hole. And as the hole moves, that leaves behind a wake of wrong bonds. And the other wave function ansatz that we considered is pi flux theory, where we are envisioning there is resonantly balanced bond state with a hole doped into it. Neither of these states have they are not distinct from the perspective of net magnetic correlations, and it's not easy to see how they will be distinct. But we were able to train convolutional neural network, CCNN, to distinguish the two phases. And then once we were able to train the neural network to distinguish the two phases, we wanted to know whether they were getting the answers right for the right reason. And that's where we introduced a regularization path analysis. So for regularization path analysis, we first fixed the architecture once the network is trained. We fixed the learned filters, and these were the filters that were learned associated with in the three of the channels, spin up, spin down, and hole. And we introduced an additional new loss, that's the cost function, which really is designed to penalize using the input. So this beta is where the convolution of each of the powers of the convolution got collected. So this n counts each of the orders of the convolution in our polynomial representation of a nonlinear function, and alpha is associated with filter. By having this loss controlled by lambda, in the limit of large lambda, the neural network would really want to minimize uses of beta because that will cost. Using the input will cost. So the neural network will try to use only the best input channel that's most informative, because it really needs to be sparing of its resources. So if we see as we dial down lambda, these plots are as a function of 1 over lambda. As we dial down lambda, increasing 1 over lambda, we will start to see more and more inputs are used. Initially, only one input is being used to make a diagnosis of pi flux, and only one input is being used to make a diagnosis of of a geometric string. By looking at which input was used, that came from the convolutional map, we can figure out, okay, if this filter at this order is making the most effective choice for the neural network, if it has to come to the right decision while being on a ration for how much input to use. So this analysis gives us insight into which inputs are most informative to the neural network once the training has been fixed. And then now we have a way of looking at the CCNN's learning and making an assessment. Was the answer right for the right or wrong reason? So here is, because the fourth order were most informative as the very first input to be used, we look at what fourth order of these filters would mean. This was a filter for the geometric string state with this wake of wrong bonds, and the lower one was a filter that was learned for the pi flux. A fourth order of these filters means we'll be looking at 4 pixels at the same time, pixels at once at each point. So if we look at 4 pixels out of these channels, we see these kind of patterns. We can make these kind of patterns. And now we can start to recognize oh, these are kind of motifs that we would have expected given our picture of what geometric string is. So what we can see here is that without us telling neural network to look for these features, these motifs, based on the feedback we were giving and the data that we gave, neural network learned to extract these specific motifs as a characteristic motif associated with the label. And this is a fourth order correlator. That's not something that we would typically look at. We look at second order correlators typically as sort of a fluctuation. But what this showed was that for this geometric string state, you really need to look at fourth order correlator to learn something meaningful and distinct. So this was all really exciting, but these were all done on simulated data. And the step of going from simulated data to real physical data is a really big step. And we've been successful in doing so recently, so I want to share that. So hybrid CCNN for RYDBERG quantum simulator snapshots, and these are actually looking at the real experimental data. And this work was done in collaboration with this group of wonderful people, especially Misha Lukin and Marcus Greiner's group members kindly shared their data with us. The RYDBERG quantum simulator works by loading the atoms and arranging them into an array, and they control the atomic distance to control the interaction strength. The interaction is long range, but there is also a transverse field-like term. So the interaction by itself can be thought of as like interaction on Ising spin, because each site has two states accessible to it, either RYDBERG or ground. But this transverse field term introduces quantum dynamics. And in this paper, the SQUARE-LATTICE model, such model was first implemented and analyzed. So from the classical computer simulations, either doing Monte Carlo or DMRG, one can, given the long rangeness of this potential, one would expect various charge order states. So these are charge order, checkerboard, star, rhombic are charge order states one can expect. And another state that was predicted in the early DMRG simulation by Ryan and collaborators was the state called striated state, where what's plotted in pink is sort of a superposition of RYDBERG and ground. Now, what does actual data that might be in these phases look like? These are examples of snapshots. Now, top would be a classical picture of a long-range order state. Snapshots look like this. These are just examples of the snapshot. This is a snapshot, which could be checkerboard, and you can sort of see checkerboard simulations here. And this is a snapshot which could be striated. This is a snapshot which could be star. But if I didn't give you the guidance above, and if I told you, well, this and this might be different, it may not be obvious to you how to tell this and that apart. Originally, what was done was to take these snapshot data and Fourier transform each one of the snapshots and average the Fourier intensities, and then look at the Fourier peaks to discern, because each of these states have different periodicities and different Fourier peaks. Fourier peaks were used to discern which phase the experimental data belong to. Rhombic phase has a very large unit cell, and experimental system is clearly restricted by the boundary conditions. And it was hard to see in the data in early analysis. Any signature of rhombic phase was not seen. So we are approaching this large data set, large dimensional data set. There are about 450 points in the phase space, that is being scanned. And at each point in the phase space, there are 250 snapshot images. Each snapshot has 13 by 13 grid of states that can be either up or down, or black or white, or RYDBERG or ground. These are projective measurements. So that is the total volume of the data that we want to look at. And we wanted to look at this in a unbiased and comprehensive way, because the what I was earlier discussing with using neural network was a supervised learning. It depends on the whole analysis heavily depends on the label training set, which introduces bias. So as the quantum simulator technologies evolve and become accessible, there could be things that we didn't know to expect happening, and we want to be able to discover what's going on in this data. So we introduced an approach that is combining the best of unsupervised world and a supervised world, and that's our hybrid CCNN. With this total volume of the data, we first go through an unsupervised learning process, which the ultimate goal of this unsupervised learning is to look at the whole phase space and group the phase space regions into qualitatively different regions. That would be the phase diagram. But we want to discover the phase diagram without specifying order parameter or specifying means of discovering it, but entirely based on whatever evolution is going on in the data. So ultimately, for this goal, we want to cluster the phase space point into different regions, these different colors. But to apply clustering, this total dimension of the data space is way too big. Then finding the manifold that is separating different regions can become complex, become difficult and unstable. So we need to first reduce the dimensionality from this total dimension. What we did was to first take the average Fourier transform and the average of the Fourier transforms at each point, reducing 250 down to 1 at each phase space point. That still gives us 13 by 13. Here, the Fourier transform was padded to be 16 by 16 dimensional space. So there are 16 by 16 points in the Fourier space, and that's still a large space. So what we did was to do a PCA to find components in the Fourier space, a linear combination of points in the Fourier space that are meaningfully changing as we scan through the entire phase space. And we then were able to reduce the dimensionality of the data space that we're going to then apply clustering on to 6 to 10 PCA components kept. Once we have this reduced dimensional space of just the top PCA components, we then do Gaussian mixture model clustering. This unsupervised learning process revealed to us there are multiple regions with qualitatively distinct behaviors. Lower three, red, blue, and green, are pretty consistent with where the regions in the phase space where manual analysis using Fourier transform and looking at the peaks resulted in different phases. But these upper region, this orange region and the purple region, was something that was totally unexpected before we went ahead and looked in this way. So this analysis revealed to us that in this data, in this pile of data, there are not 3, but 5 different regions, including featureless regions, 6 different regions in the phase space. Now we wanted to know how they are different. They are supposedly different, but how are they different? Now that's where we want to be able to do the interpretation in terms of physically insightful correlations. That's where we do supervised learning. Because this map obtained with unsupervised learning informed us there are 5 phases and where they are roughly located. We use this as an input for choosing training point. There are 5 sets of 5 training points chosen. We choose these 5 training points, and now we go through CCNN to discover what are the meaningful features. So the unsupervised test gave us these 3 phases, matching pretty well with the checkerboard star and striated that was originally reported. And now we're going to go through supervised learning. First, supervised learning pass gave us some insight, but we quickly learned there is a boundary effect in this finite size data. Although the boundary effect is not what one would look for if you want to infer information relevant for thermodynamic limit, in interpreting measurements which are done on this quantum simulator data on a physical system, which are subject to boundary conditions, it is important to be able to tell apart from data what is boundary and what is bulk. So in order to be able to learn boundary effect or any other sort of consistently occurring spatially structured information beyond the scale of the filter, we introduced this spatial weighting. So the supervised phase diagram gave us, in addition to these 3 phases that was reconfirmed, 2 new phases. These were identified by the CCNN that's as it was to be consistent with unsupervised learning results. The first thing that we've noticed was this region, which was earlier named striated. It was a phase that is expected to have quantum dynamics embedded in it because these light pink regions are supposed to be in superposition. But earlier analysis using average Fourier intensities could not point to any aspect that is sort of quantum mechanical. Because our supervised learning approach looked at each of the snapshots separately, we can look for fluctuations from snapshot to snapshot. And that by watching how those fluctuations evolve, we were able to gain a sense of entanglement in this striated phase. Entanglement in the sense of there being clear correlation among these states, that these 2 sites are simultaneously turning on, and these 3 sites show the right kind of correlation as this being in a superposition of up and down. And that was the first insight into the phase that based on the DMRG simulations were anticipated to be of this kind of sort. But from the data, experimental data itself, there was until now no clear indication of in what way is it a state that involves superposition. And now from the CCNN analysis, we can put our finger on it because we can say that, well, these are the signs of these correlations are reflecting the fact that this has to be in a superposition and forming this structure. The new phase that we learned, of the 2 new phases we've learned, the first is the edge ordering, which was learning of which was enabled by this spatial weighting. The spatial weighting that was learned to be of this structure, which is really consistent with every single snapshot that we look at. The snapshots are showing this Z2 ordering at the edge. And this entire phase is characterized by having Z2 ordering at the edge and the bulk being rather disordered. And this sort of heterogeneous feature was would invoke the notion of first order phase transition. And so there are several phases on this side. Some of those are expected to be first order, but some of those were expected to be second order. Having this edge order phase extended all around raises new questions about how, why, what could be a second order transition is possibly behaving as first order and giving the phase separation. The next new discovery was correlations signatures of the rhombic phase. It's in this purple region. Now, if you take the experimental data and Fourier transform and average the Fourier transform, it's this blurry thing that comes out. If one had ideal rhombic phase, one should have something like this. First hint that this region is associated with rhombic phase actually came from the unsupervised learning, because the component, PCA component that was learned has this kind of structure, which is reminiscent of this ideal rhombic. Although the full data set is like this, the PCA component was like that. But it was really looking at the CCNN and interpreting what was learned that gave us more confidence that we are learning motifs that would build rhombic phase if given enough space to build it. So these are the two filters that were learned. And from the third order correlation and the second order correlation, we can look for these kind of features to be key features associated with rhombic phase for this filter and this other filter. And now we can see why these would be relevant for rhombic, because if we take an ideal rhombic pattern, we do see those motifs. Especially these triangles are everywhere, and these blue bonds are between the two triangles. Now, is that actually in the data? So these are the snapshot data, and we can actually find in the snapshot data some of these motifs. To label this data to be rhombic requires, in a way, having an insight into how to break down long-range order rhombic into small motifs that could fit in despite the edge effect in this finite size system. And all of these, some of these are unique to the rhombic phase, and that's how we can work our way backward, learning, taking this data, learning these correlations, and then recognizing that some of these motifs are only pieces available to the rhombic phase. My time is almost up. I talked about using machine learning to interpret and infer quantum simulation results. And this is because now the scale of the quantum systems are reaching the range that is well outside the reach of any kind of tomographic methods. They are still very noisy, but they are starting to approach a regime where they can do interesting things. It's really critical time for there to be methods that can allow us to learn from, reduce that simulation data, snapshots, volumes of the snapshots, into information that we know how to think about. And I've talked about supervised machine learning, learning characteristic correlations using interpretable CCNN, and hybrid machine learning, combining unsupervised learning based phase diagram discovery phase with interpretable supervised machine learning phase, where we learn the identities, characteristics of each phase. Ultimately, these are tools to reduce the data into something that we can process. And it might be possible to not use these new tools to look at this new data, just like it is possible to drill a hole with a hand crank drill. But having these approaches that are specifically developed for large dimensional data and large volumes of the data would be ideal for carrying out more efficient task of getting to our objectives, but also some of these tools, power tools, can be adapted for different purposes. So right now we are using the hybrid CCNN and CCNN-based approaches to actually try to understand what's going on in quantum spin liquid data from DMRG simulations. And it's just a new perspective to try to learn from the projective measurements of wave functions. Wave functions are big and complex objects, and projective measurements are one way to look at them, and it's actually a very relevant way to look at them, given where we are in the development of quantum simulators. So with that, I want to end my talk, and thank you for your attention.